explaining basic 3D theory. This article explains all of the basic theory that's useful to know when you are getting started with working with 3D coordinate system. 3D essentially is all about representations of shapes in a 3D space with a coordinate system used to calculate their position. And if you have taken some geometry class, or if you are an engineering student and have taken calculus 3, you have dealt with the 3 dimensions. So we have the horizontal, the x representation, the vertical, we have the y representation, and then we have the z representation. WebGL uses the right hand coordinate system. The x-axis points to the right, so you can see here the x-axis points to the right, the y-axis points up, so you have here up to this point you have 2D, and the z-axis points out of the screen. So if you have taken maybe a physics class and you have dealt with the thumb rule, okay, so if you point your thumb towards you, that would be like the zx points. So the zx points out of the screen as seen in the above diagram. So we have that. Objects. Different types of objects are built using vertices. A vertex is a point in a space having its own 3D position and the coordinate system, and usually some additional information that defines it. Every vertex is described by these attributes. So we have position, coloring, normal, and texture. Okay, position identifies it in a 3D space. So we have the x, y, and z coordinates. We have the color, holds an RGBA value, R, G, and B for the red, green, and blue channels, alpha for transparency. All values range from 0.0 to 1.0. Normal, a way to describe the direction that the vertex is facing. Texture, a 2D image that the vertex can use to decorate the surface it is part of instead of a simple color. You can build geometry using this information. Here's an example of a cube. So we have this cube here, and as you can see we have in all these corners we have the V1, we have the V2, V3, V4, V5, V6, V7, and then these planes pretty much are the faces. So we have a face here, another face here, another face here. A face of the given shape is a plane between vertices. For example, a cube has 8 different vertices, points in a space, and 6 different faces, each constructed out of 4 vertices. A normal defines which way the face is directed in. Also, by connecting the points, we are creating the edges of the cube. Geometry is built from a vertex and the face, while material is a texture, which uses a color or an image. If we connect the geometry with the material, we will get a mesh. So maybe if you have dealt with MATLAB, you have familiar with meshes or mesh. Rendering pipeline. The rendering pipeline is the process by which images are prepared and output onto the screen. The graphics rendering pipeline takes the 3D objects built from the primitives described using vertices, applies processing, calculates the fragments, and renders them on the 2D screen as pixels. So as you can see here, we have the vertices, we have this vertex processing, we have this we have the vertices, we have the primitives, the fragments, process fragments, and the pixels. So here in these vertices we have the vertex processing, we have this 3D primitives, rasterization, so we have the 3D fragments, then we have the fragment processing, 3D process fragments, and then output merging at 2D pixels. Terminology used in the diagram above is as follows. A primitive, so we're talking about this one, the second image. A primitive, an input to the pipeline. It's built from vertices and can be a triangle, point, or line. Okay, so a fragment, this one. A fragment, a 3D projection of a pixel which has all the same attributes as a pixel. Now here, this one, the pixel, this computer here, this cube inside of the computer. A point on the screen arranged in the 2D grid which holds an RGBA color. Vertex and fragment processing are programmable. You can write your own shaders that manipulate the output. Vertex processing. Vertex processing is about combining the information about individual vertices into primitives and setting their coordinates and the 3D space for the viewer to see. It's like taking a photo of the given scenery you have prepared. You have to place the object first, configure the camera, and then take the shot. Okay. So here we have the vertices, so we have these points, and then we have the primitives. So from the vertices to the primitive, this is the vertex processing. So you have 3 dots here, then you put 3 lines, and then you have your 3D elements. So you go for the vertices to your primitives. There are 4 stages to this processing. The first one involves arranging the objects and the world, okay, and it's called model transformation. Then there is view transformation, which takes care of positioning and setting the orientation of the camera in the 3D space. The camera has 3 parameters: location, direction, and orientation, which have to be defined for the newly created scene. Okay, so we have the orientation, we have the direction, and we have the location. Okay, so the camera. Now, projection transformation, also called perspective transformation, then defines the camera settings. It sets up what can be seen by the camera. The configuration includes fields of view, aspect ratio, and optional near and far planes. Read the camera paragraph in the 3.js article to learn about those. So as you can see, we have this point here, then we have the f of b, we have near, far, and then we have the height and also the width. Okay, the last step is viewport transformation, which involves outputting everything for the next step in the rendering pipeline. Rasterization. Rasterization converts primitives, which are connected vertices, to a set of fragments. So this is rasterization. Now we're gonna go from primitives to fragments. So we have this 3D image. So you have these points here connected, these dots connected, and the process that is gonna go from primitive to fragment is gonna be the rasterization. Those fragments, which are 3D projections of the 2D pixels, are aligned to the pixel grid, so eventually they can be printed out as pixels on a 2D screen display during the output merging stage. And now we have the fragment processing. Fragment processing focuses on textures and lighting. It calculates final colors based on the given parameters. So we have these fragments here, this 3D, and now the process is gonna be the fragment processing. So it's gonna be it's gonna be a 3D, but it's gonna be a process fragment. So pretty much the same, but we are adding color. Textures. Textures are 2D images used in a 3D space to make the objects look better and more realistic. Textures are combined from single texture elements called texels, the same way picture elements are combined from pixels. Applying textures onto objects during the fragment processing stage of the rendering pipeline allow us to adjust it by wrapping and filtering if necessary. Okay, texture wrapping allows us to repeat the 2D image around the 3D object. Texture filtering is applied when the original resolution or the texture image is different from the display fragment. It will be magnified or magnified accordingly. So we're almost done with this article. Then we have the lighting. The colors we see on the screen is a result of the light source interacting with the surface colors of the object's material. Light may be absorbed or reflected. The standard font lighting model implemented in WebGL has 4 basic types of lighting. So we have diffuse, specular, ambient, and emissive. So diffuse, a distant directional light like the sun. Specular, a point of light just like a light bulb in a room or a flashlight. Then we have ambient, the constant light applied to everything on the scene. Finally, the emissive, the light emitted directly by the object. Now, output merging. During the output manipulation stage, all of the fragments of the primitives from the 3D space are transformed into a 2D grid of pixels that are then printed out on the screen display. So here we have process fragments, we have the 3D, and then we have the output merging. So it's pretty much changing from this 3D as we are changing it to 2D and pixels. During output merging, some processing is also applied to ignore information that is not needed. For example, the parameters of objects that are outside of the screen or behind other objects and that's not visible are not calculated. So the conclusion: now you know the basic theory behind the 3D manipulation. If you want to move on to practice and see more demos in action, follow up with this tutorial below. So we're gonna see some of those later on.